Hello everyone and welcome to your final recitation for CS 1332. It's been a wild ride, but this is the end for you guys. Fortunately, hopefully it's been a happy journey, even though it's been a rough one. Something to note is also for Landon and I, this is most likely the last recitation that we are ever going to give. So thank you. It's probably not how I anticipated that this would be, but you guys have been very great and very flexible in helping us do everything, and I seriously want to thank you guys for that. Since they just sent out the little survey thing yesterday, I filled it out. Frankly, it's not as useful to us as I would have liked it in terms of like actually giving feedback to your instructors. So I will say that if you have TAs that helped you a lot on Piazza or helped you through these virtual office hours over these last couple of weeks, or you had your recitation TAs that you really loved and then you never got to really say thank you to them because then we all went online, please fill out the CTL thank a teacher thing for them. It really means a lot to us to receive one of those, so please, if you never got the chance to say thank you to them, or they've been helping you a lot now, please fill that out to let them know that you really enjoyed being a student under them. Sorry. It really means a lot to us. Thank you guys. With that said, let's get started today. We've got a couple things we're going to talk about. First thing is going to be Prim's algorithm. That's the last graph algorithm that we never really got to talk about. It's kind of an alternative version of Kruskal's, well, an alternative to Kruskal's for MSTs. Then we're going to do final exam review. Thank you guys for filling out that form we sent out, giving us some topics. The top choices, just so you guys know in advance, were Kruskal's, LCS, and Quicksort. So those are the first three I'm going to go over, and that's probably going to take me most of the time. If we somehow manage to finish all those and have a lot of extra time left, I might talk a little bit more about Dijkstra's, but we'll see when we get there. As always, if you have any questions, feel free to submit those over Piazza, and our wonderful two TAs will go ahead and forward those to me. Definitely, this is a good day for a lot of questions because this is intended to mostly be review for the final. I'm also not going to talk too much about the final on here because we've released a lot of Canvas announcement stuff about that, and that's a lot more accurate than I'm going to be. With that said, let's go ahead and get started with some Prims. So, as I mentioned earlier, Prims is another MST algorithm. So, just in case people don't remember exactly what an MST is, remember that's when we have a graph and we essentially want to connect all of the vertices using as little weight as possible. Without making any cycles, we want it to be a tree. That's what the T in MST stands for. Okay. So we talked about last week how we can use Kruskal's algorithm to do this by using the disjoint set, putting all of the edges in a priority queue, but there is another way to do it. And I mentioned that we talked a lot about BFS algorithms. Well, we can use that for this too. So Prims is a variant of BFS and is another greedy MST algorithm. I didn't really talk a lot about what greedy algorithms meant in the last couple weeks. Essentially what that means is it always assumes that the best step you can take at your current time is always the correct step to take. You'll learn a lot more about greedy algorithms specifically in CS 3510 or 3511. It's just kind of an idea of you're encountering a couple of greedy algorithms right now. It's, as a trivia point, it's actually why Dijkstra's doesn't really work for negative edges very well, because it assumes that you're not going to have a better path down the line, which you can have with negative edge weights. Okay, so if Prims is a variant of BFS, it's going to need a couple things. It's going to need a frontier, which tells us what things to look at next. It needs a visited set to tell us what we've already looked at, and it needs some sort of structure to return. Those are kind of the three fundamental parts of a BFS. So, for what we've already seen, that's just going to be a visited set. And the visited set is going to keep track of all of the current vertices in our MST. So as we incorporate new vertices into our MST, all of those are going to go in the visited set. Also, one thing I can add on here. We're going to need a starting vertex too. Just like Dijkstra's BFS, DFS, we need a starting vertex for Prims. We didn't need one for Kruskal's, I will note. So we have our visited set. Then for our frontier, just like Dijkstra's, we're going to use a priority queue. The priority queue is going to determine which edges we visit next. And I underline the word edges here because I do mean we're actually dealing with edges. In Dijkstra's, you could use those like vertex distance objects. BFS, DFS, you just needed vertices. Prims, you do need edges. You can't just get away with using a vertex distance. The reason you need edges is because we need to return a set of edges. So instead of returning a list like in BFS DFS or a map like in Dijkstra's, Prims is going to return a set, just like Kruskal's, and this set is going to store all of the edges in our MST that we return at the end. And the reason, because we're storing edges like this, that's why we need to have our priority queue hold edges in them. Remember that priority queue is going to be kind of sorted by the weight of the edge with the lowest weight edges at the top, which is useful for forming a minimum spanning tree. So this is the basic outline of our algorithm. Let's take a look at what it actually looks like in a little more detail. So this is the basic algorithm of Prims. First thing we do is we choose a starting vertex, which is usually given to us, and we mark it as visited. Remember that marking something as visited just means we're adding it to the visited set. That visited set gives us O of 1 contains, so it's really fast to check if a vertex is already visited, as long as we're using a set like that. Next step is we're going to enqueue every edge adjacent to our start vertex into the priority queue. So that's just if our start vertex is like here and it has like a bunch of edges going off of it with a bunch of like weights, all of those edges are going to go into the priority queue. Then we'll sort them out and deal with them later, but that's how we're going to initialize our algorithm. Note that Kruskal's put all of the edges in the entire graph into the priority queue. Prims just puts the ones adjacent to our start vertex. That's the important distinction. Then we start our main loop. This should look familiar to you. We're looping while our priority queue is not empty, and we haven't found a valid MST. It's the exact same loop condition that we used for Kruskal's algorithm. I'll remind you that no MST found means that the size of our MST is not v minus 1 or 2v minus 1, because you'll remember that that is the number of edges a valid MST should always have. So this can just be a simple O of 1 size check. Nothing else we need to do with that. You could also do this exact same check with the visited set size. You could check if your visited set contains all the vertices in it, and that would be another valid way to do this check. Those both work for Prim's algorithm. So, then what do? We're dequeuing something from the priority queue. You'll note it's an edge, not a vertex. So I'm marking that edge as u comma v. It's not just one vertex, it's two. We do need both of them because we'll need to include both of them in our MST. Then, just like in all of the other algorithms, we're checking if something isn't visited, but here we have two vertices. The important thing is that we're going to check if that end vertice, v in this case, if that one isn't visited. And that should make sense to you. Think about like how we initialize this algorithm. We have the start vertex, which is automatically visited, and all of the edges adjacent to it. So this might be like A, B, A, C, A, F. So this first one, when we do our first dequeue, U is always going to be something we visited, but V is going to be kind of the new thing we're going to. So we check if a V is not visited. If we find that it's not actually a visited vertex, we're going to mark it as visited, add it to our returning object, in this case that's our MST. Note we add the forward edge and the reverse edge. That's just because we normally use kind of directed edges even if the graph itself is an undirected graph. This is mostly just an implementation detail, but the basic idea is you're adding the edge to your MST. That's what's going on in this step. Then, this is a little weirdly written loop. For every edge VW adjacent to V, this is just like here we said all adjacent edges to the start. This is all the edges that are adjacent to V. So we're kind of branching out from our new vertex. We're going to enqueue it to our priority queue as long as it doesn't go back to a vertex we've already seen. So how do we check if it's gone back to a vertex we've already seen? That's checking if W, so the second part of this edge, if that vertex is not visited, then that means it's going to a new vertex. So we enqueue it to the priority queue. Now, a big difference I want to note between Prims and Dijkstra's, because Dijkstra's worked very similar to this. In Dijkstra's, we enqueued edges using a bunch of like cumulative weights. We kept adding the weights on together. In Prims, we don't add up the weights at all. We just enqueue the edges with the same weights they have. You can actually pretty much turn Dijkstra's into Prims in just a couple change lines. You just change the maps to sets, and you change this enqueue to not add up weights. and you'll get prims. It's really cool. This is why BFS is such an important algorithm to learn well. So we enqueue all our neighboring edges to the priority queue, and then we repeat this loop. And that's the main idea of prims. Now, just like Kruskal's, we have one more step at the very end. We need to check if the size is valid before returning. So I wrote this out in Kruskal's. I didn't really write out the full thing here. You're just checking if the size of that MST is v minus 1 or not, or 2v minus 1. If it is, perfect, return it. If it's not, you just return null to indicate that there's no valid MST. That only happens when you're dealing with a disconnected graph, where it wouldn't have been possible to actually create an MST out of it. The priority queue in that case would empty before you found an MST. Note that the priority queue emptying doesn't mean that you don't have a valid MST. It's the MST's size not being correct. You always check the size. Because it's possible, as I mentioned last week, it's possible that both of these happen at the same time, in which case you do have a valid MST. So this is the easier condition to check. In terms of efficiency, this algorithm, I already mentioned, it's incredibly similar to Dijkstra's. We're adding things to a priority queue, dequeuing them, putting them in a bunch of sets. So our efficiency is going to be the exact same. That O of v plus e log v, it's the same as Dijkstra's for the exact same reason. The reasoning is a little complicated and a little above the scope of this class, and not really in a fun way like Kruskal's. So it's not really going to be something we press you guys on too hard to know exactly like why this efficiency is what it is. But this is Prim's efficiency. Now I'll give you guys a little bit to ask some questions for me, and I will try to answer those. Otherwise, we will move into the visualization tool for an example. So if you want to pull that up, it should be the default graph for prims. I'll get to that in just a second. Okay, I got a question of when would I use prims over Kruskal's or vice versa. So those are excellent questions. There's a couple different situations for them. So a neat detail is so in this class we mentioned that we're only talking about MSTs for undirected graphs. But what if you actually wanted to use a directed graph to find your MST? Well, in that case, prims can sometimes give you some meaningful output from a starting vertex as to what an MST can be, because you can actually like have a tree starting from one vertex and branching out, versus Kruskal's is just going to kind of put edges together in meaningless ways. You'll note Kruskal's does kind of have a slightly better runtime than prims, so it works better in a lot of other situations. Kruskal's, I believe, also does actually work kind of well with negative edge weights. I'm not going to say it works flawlessly, but prims will not work at all with negative edge weights. Kruskal's actually could. Also, if you had like if you really wanted to kind of build like a partial MST starting from a start vertex, obviously prims lets you choose a start vertex that you want to branch out from, versus Kruskal's just kind of goes all over the place. Or if you had a graph where you needed to include certain edges in your MST, regardless of whether they were actually like good to include or not, Kruskal's is good because you can kind of force those edges in your MST, initialize the algorithm that way, and then build the MST from there. So there's kind of a lot of little pros and cons between them. If you're just looking to find an MST with no strings attached, it doesn't really matter which one you use, they're both about the same. Excellent question though, thank you for asking it. With that said, I'm going to pass it over to the visualization tool, and we're going to run through an example of prims. And I will be able to show you one other detail about prims that's kind of hard to explain without showing you the example. So this is our graph. Let's go ahead and run it starting on A. So, as I mentioned, our first step is to add A to our visited set. Now we're going to add all of the adjacent edges into our priority queue. And we see we get these two edges right here. Now something about prims that people often describe is people kind of describe it as choosing edges along a cut. And I'll do my best to kind of show what that means, I really wish I could like draw on this screen, but I don't think there's a good way for me to do that, and I don't have anything set up for it right now. But kind of try to imagine a imaginary line that's cutting A off from the rest of the graph, so kind of along where my cursor is going right now. That is the cut that some people talk about in prims. And you'll notice right now there are two edges going over that cut. And what we're going to do is we're always going to take the smallest weight edge that crosses over the cut. That's the basic idea behind how prims works. And if you wanted to kind of have some intuition as to like why prims works, this cut strategy kind of helps to prove it. So we've got this weight 1 and weight 5 edge that cross over our imaginary cut. So the weight 1 edge is what we're going to end up picking. That's that AB. You'll notice that this destination B, where that's the one we're going to check. It's not a visited vertex, so we can add this edge to our MST and add B to the visited set. Now we can add all of these adjacent edges into our priority queue. You'll note we look at this one too, but A has already been visited, so we skip it over. But this BC, BD, and BG edge are all going to go into our priority queue. So now before we dequeue, obviously we're going to dequeue this BG1 edge next, but let's think about it in terms of the cut. Our cut no longer looks like this because we don't just have A in our MST. Now we have to draw the cut more like this. So it has to go and cut off A and B from the rest of our graph. And we see that 4 edges go across this cut. The weight 5, the weight 7, the weight 1, and weight 9. Obviously the weight 1 is the cheapest, so that's the edge that we're going to take next. We dequeue it. G isn't visited, so we add this to our MST, and then we visit G. Now we're going to look and add all of those adjacent edges into our priority queue. Obviously this edge is already visited, but these 4 edges are not. You'll notice everything just gets reordered automatically in the priority queue. So now everything is enqueued into our priority queue. So now is when the cut starts to look a little weird, because it's kind of hard to draw a cut in the middle of this. So if we wanted to cut this, you imagine the cut kind of has to go like over here and then around G and then back to A. The basic idea is the edges going across the cut are the ones connecting the vertices in our MST to the rest of the graph. So in this case, it's always going to be most of the edges in our priority queue. And in this case, right now, it is the edges in our priority queue. But you'll see later that sometimes it gets a little different. So right now, the cheapest edge across this cut is this FG2. So we look at this. In this case, we see that F is not visited. So we add it to our MST in our visited set. We've got these 3 adjacent edges right here. This one is already visited because we visited G, but this D and H are both going to go into our visited set. And now our cut, again, looks a little weird. It kind of goes across this and then around to here. So the cheapest edge is obviously this FH0. So that's what we dequeue. H is not visited. So we're going to go ahead and add the edge and then add the vertex to the visited set in the MST. And then we enqueue this one edge right here. Or sorry, we would enqueue this edge, but you'll notice that G is already a visited vertex, so there's no point in enqueuing this edge because it goes to some place we've already been. So what does our cut look like now? Well, now we go completely around this way. And you'll notice that this GH3, that edge is in our priority queue right now, but you'll notice it no longer crosses over the cut. And if we think about that, what that means is that edge connects 2 vertices that are already in our MST. So if we added it, it would just create a cycle. And that's what thinking about it in terms of this cut way avoids, is any edges that don't cross over the cut would create a cycle. So when we dequeue this edge, we'll see that H, the destination, is a visited vertex, so we skip this edge completely. And now we look at the actual cheapest edge which crosses this cut, which is this DF4. D is not visited yet, so we add the edge and the vertex to the visited set. Both of these edges are going to get skipped over because B and F are visited. And now, I'll step back one. Now we look at our cut. now the cut goes over here. It really only hits these 4 edges. So this DB9 is no longer crossing over the cut. So when we get to this edge, we're just going to skip it. But for now, we're looking at this AC edge. We can look at that. C is not yet visited, so we add the edge to our MST. We add the vertex to our visited set. We NQ the adjacent edges. So this one gets skipped, this one's going to get skipped, and this one's going to get skipped. So nothing actually gets added here. Now we look at our cut, and the cut is relatively simple. It just crosses over this one single edge. So that means all of the other edges in our priority queue are just going to end up getting skipped. Sorry. All the edges in our priority queue are just going to end up getting skipped, and this is obviously the next edge we're going to have to take. But in terms of the algorithm, we obviously don't know that. So we dequeue this edge. C is visited, so it's skipped. We dequeue this edge. D is visited, so it's skipped. We dequeue this edge. E is not visited, so we add the edge. We add E to the visited set. And now we can kind of see our stopping conditions. 2 things really happened at the same time. So our question, I'll get to that in a second. So if we count the number of edges, there's 1, 2, 3, 4, 5, 6, 7 edges in our MST right now. And we have 8 vertices in our graph. So we have V minus 1 edges. And that means that we've created a valid MST. We can also look at the visited set and see that there's 8 vertices in the visited set and 8 vertices in the graph. Both of those tell us that we've already found a valid MST, so there's no point in dequeuing this edge because it can't help us anymore. So the algorithm is going to terminate right after this because of both of those conditions. Then I just saw 2 questions. In the online video, the efficiency of Kruskal's is E plus V log V, while in last week's recitation I said it is E log V. Which one should get used in the exams? In the exams, you should use E log V, what I said in last week's recitation. I don't believe we'll ask about it. Don't quote me on that. But E log V is the correct efficiency of Kruskal's. If you want to know why, I did a kind of fun proof of that at the end of my recitation last week. So if you only watched Landon's or didn't watch them at all, I recommend kind of just checking out like the last 10-15 minutes of my recitation. And I go over a kind of interesting proof of Kruskal's. I talk about some really large numbers. It'll be kind of interesting. Another question, for our purposes, is the condition for Prim's graphs with only undirected edges? So we're not going to talk about MSTs for directed graphs in this class. We're just only ever going to talk about it for an undirected graph. As for the actual stopping condition, usually graphs are implemented with directed edges, even if it's an undirected graph. So you would use that 2 times V minus 1 stopping condition. But it really depends on your problem domain. If you had to implement it on your homework, it would have been 2 times V minus 1. On an exam, it's hard to say because you're not going to have to write code for it. But the real condition is, do you have the correct number of edges, or have you visited all vertices? And again, in this class, we're only going to talk about MSTs for undirected graphs. In other classes, you might talk about directed graph MSTs. Excellent 2 questions, though. So I will wait a little bit more in case there's any other questions about MSTs, but that's all, or about Prim, sorry. But that is all of the new content we're going to be covering in recitations. The rest of this recitation is going to be talking about review, starting with Kruskal's, moving on to LCS, and then finally, maybe finally, Quicksort. So I will give you guys some time to ask questions and then get right back. Okay, let's go ahead and get back to our regularly scheduled teaching. So let's talk about Kruskal's. So I'm not really going to go in depth with the actual like algorithm of Kruskal's because there's resources for that. B, I talked about it in last week's recitation, and those videos are up in the media gallery on Canvas if you want to rewatch them. So I don't think it's a great use of time to go and like rehash the exact algorithm for Kruskal's. But what I am going to do is I'm going to do another example, and I'm going to do the example this time on the actual board instead of using the Viz tool. To be clear, what is the distinction between Prims and Bfs? That's a question we just got. So Bfs uses a regular first in, first out queue as its frontier and returns a list of all the visited vertices in the order you visited them. Prims uses a priority queue as its frontier that is weighted using the weights of each edge and returns a set representing the MST form of the graph. Really, the only actual difference between those is the queue versus priority queue, but the slight distinction of what they're actually returning. But yes, Prims and Bfs are very similar. You'll see a lot of the similarities between these algorithms if you take a class like CS 3600. The first homework, I think you have to write a couple different graph search algorithms, and if you write them correctly using Bfs, you can transform it into DFS and then Dijkstra's, changing like one line of code. It's really cool, actually. So, now let's talk about Kruskal's. So you'll see here I've written out a graph. I think it's the same one as last week, but I'm going to kind of try to cover it in good detail. And I've written my priority queue out here of all of the edges. I've already kind of pre-sorted the edges, so I don't need to worry about accidentally choosing the wrong edge, because that would be kind of embarrassing. So the first edge we look at is this FH. Right now, nothing is a part of our MST right now. Everything is separate. When we dequeue this FH, what we do is we take these two vertices and we say, okay, if I add this edge into my MST, would that create a cycle in my current MST? Obviously, for the very first vertex I'm talking about, the answer is no. It's impossible for me to make a cycle. So this edge can get added to my MST. That shows up okay. So now my MST it's not really going to start as one tree. It's going to start as a bunch of different smaller things and merge together. You'll see what it looks like when I add more edges. Another question. If height is not stored, to find the height of a 2-4 tree, would it then be O of log n, since all leaf nodes are on the same level? We don't need to traverse for all nodes like we do for all other tree types. Exactly correct. Because we know all the leaves are on the same level, we only need to go down one path of the tree to get our height, instead of having to traverse the whole tree, even though we're not actually storing the height of each node like we would in an ADL. Excellent question. Let's get back to Kruskal's. Next edge we're going to talk about is this AB. You'll see that edge is up here. So now I ask the question, would this edge create a cycle? Well, right now the only way to actually create a cycle would be to link F and H back together some other way. So obviously the second edge isn't going to create a cycle either. So that now gets added to my MST. I'm going to actually scribble it a little bit. That makes it a little easier to see. Next up is going to be BG. So the question, does this create a cycle? Well, this edge doesn't create a cycle from A or B. There's no way to go around in a circle there. It doesn't create a cycle with F and H. So I know that BG is good to add to my MST. Now I look at FG, and the question, does FG create a cycle? Well, now this is kind of more of an actual question, because you can see ways that I could create a cycle in this graph. If I connected A and G together, that would create a cycle, for instance. So I need to be careful for all of these edges that I'm adding. Am I creating a cycle by accident? In this case, the answer is no. By connecting these two, there's no cycle in this graph. I can't start anywhere and get back to where I started. So I dequeue FG, and that edge gets added onto my MST. And now you can see there's a lot of cycle potential in this graph. If I connected these two vertices, that would be a cycle. These two, these two, these two. There's a lot of different vertices I could connect and make a cycle. So we're going to have to be careful about that. And what a surprise, GH is the next edge. So when I look at GH, I look at this edge and I say this edge, if I added it, would create a cycle in my graph. I could start from G, go to F, go to H, and then go back to G. That would be a cycle. And remember, since we're creating a minimum spanning tree, trees are acyclic. They're not allowed to have cycles in them. So I cannot add this edge into my MST. Doing so would violate the tree property. So I'm going to kind of give this a big red X to indicate that we chose not to add it to the MST because it would have created a cycle. Let's move on to our next edge. It's going to be DF. DF here does not create any cycles because D isn't connected to anything else. So I can go ahead and add that to the MST. If you have any questions about stuff while I'm teaching, feel free to go ahead and ask those. I will get to them when I'm free. But don't be afraid of asking questions early while I'm talking. Next edge is AC. That doesn't create any cycles in our current MST. So we can DQ it. And then we can add AC. Next up is BC. But if we look at BC, if I connected these two, I would have a cycle from B to A to C back to B. So when we DQ BC, we're going to ignore that edge. So again, I'm going to cross it out in red to indicate that we ignored it. Next up is BD. But if we look at BD, that creates a cycle from B to G to F back to D, then back to B. So we're not going to look at this BD edge either. Or we're going to look at it and ignore it, sorry. Next up is GE. E is not connected to anything, so obviously this does not create a cycle. Oop, dropping my marker doesn't help. So we DQ GE. And then we add GE into our MST. And now, before we DQ GC from the priority queue, we can look at what we've created. Right now there's 1, 2, 3, 4, 5, 6, 7 edges currently in our MST. And since we have 8 vertices, we would expect 7 edges in our final MST. So we know that we've already created a valid MST, and there's nothing more we need to look at. We're completely done. So I don't, like this GC edge doesn't even get a red X. We didn't look at it and ignore it. We just didn't look at it. So this is kind of an example of how Kruskal's works. Hopefully I ran you through the process, but the overall idea is very simple. You order the edges from smallest to largest, and then in turn add every edge that doesn't create a cycle. That's kind of the basic concept of Kruskal's. Now again, I'm going to give you guys some time, and oh yeah, I can write this because someone asked about it earlier. It is O of E times the log of V. That is our efficiency. So a question. So I get that we are checking whether a new vertex can be added without forming cycles. I know this will probably not be on the final, but what would the backing structure be for checking if 2 vertices are connected? What is the big O of checking connectedness? Excellent question, and I encourage you to watch last week's recitation. The answer to your question is there's 2 answers because you asked 2 questions. The first answer is we're using a structure called a disjoint set to tell us whether 2 vertices are connected. And what that disjoint set does is basically we can give the disjoint set 2 vertices, and it will tell us if those 2 vertices are currently connected or not. So at the start of the algorithm, it says no, none of the vertices are connected. It also gives us the ability to actually connect vertexes together. So we use that data structure in order to do all this checking connectedness. What is the big O of checking it? So that's, I encourage you to watch last week, but that's where the alpha came in. So the big O of all of these checking connectedness overall is E alpha V, where alpha is the inverse Ackermann function. And I encourage you to look at last week's recitation, or you can find things online that talk about what the inverse Ackermann function actually is, but it's completely smaller than log V, so it's ignored in the overall efficiency. Good questions, though. Another question, would Prim's algorithm be faster than Kruskal's in a very dense graph? Usually yes, because Kruskal's always kind of orders all of the edges and then really has to look through them one by one. And if we have a really dense graph, that's a lot of extra edges we're going to look at. In all of looking at each of those edges is a priority queue dequeue operation. So we kind of waste a lot of time dequeuing edges. Versus in Prims, we avoid enqueuing a lot of those extra edges because of our visited set. And looping over the edges and checking the visited set is a lot faster than dequeuing things from a priority queue. So we can save a lot of time there. So yeah, that's a good example of when Prim's algorithm might be a little bit faster. Great questions. I will leave it up for another little bit for you guys to ask more questions about really Kruskal's, Prims, or other graph algorithms, because the later stuff I'm talking about is not graph algorithm based unless I have time to get to Dijkstra's, which I don't find likely. So I'll leave it up for a bit to ask a couple more questions, and then I'll move on to the longest common subsequence algorithm. Sorry about that, I had to respond to someone real quick, but I don't see any new questions. So I'm going to go ahead and move on to the longest common subsequence algorithm. Because a lot of people had questions about this. Kruskal and LCS were by far the top 2 votes from our poll that we sent out. Thank you guys for filling that out, by the way. It's really useful to get feedback like that. So, again, just like before, I'm not going to really talk about the algorithm because A, you don't need to code it. B, you can find it on the Viz tool. C, you can find it in like our slides and stuff. D, you can find it in last week's video. And E, it's just easier for me to show it like this. But again, I am going to do the example actually on the board instead of using the Viz tool because I think it'll make it a little easier for me to actually kind of write out the things I want. So we've given this LCS table right here, and you can see that we're trying to find the longest common subsequence of survivor and service. And I've drawn out this grid, and again, you'll note important things. I have this empty string column and this empty string row. Those are important. Another question, how do you check if a cycle is about to be formed in Kruskal's? So that's using the disjoint set operations we talked about last week. If you call find on 2 vertices and get the exact same answer, then that means if you wrote an edge between them, it would create a cycle. So that disjoint set lets you check in amortized alpha n time that you're about to create a cycle. But it does use those disjoint set operations, and I'm not going to talk in detail about how the disjoint set works right now because it's not really relevant to this class. So I have this empty string column and this empty string row, and this allows me to fill out my base case. I'm going to use a different marker for this because it should be a little easier to... I'll stick with this one. Remember that the longest common subsequence of anything in the empty string is 0, like the 0 length string, the empty string itself, because there's obviously no way that you can share a character with nothing. So that means I can fill in that this first row is going to be all zeros, and this first column is going to be all zeros. I guess this is kind of confusing. This is the letter O, and everything else in these tables is going to be the number 0. Sorry if that ended up being confusing for anyone. Is that another question? No. Yes. Okay. So the question is adjacency matrix versus adjacency list. Could I speak a little bit about the difference between these two and their efficiencies? Good. So the adjacency matrix is just a big table with all of the vertices on both axes. And the table is filled out with spots if we have an edge connecting those two vertices. So what that means is, if I ask you, is there an edge between vertex A and vertex D? You can tell me an O of 1 time just by pointing at like that spot in the table, yes or no. It's very easy to check if if an edge exists using an adjacency matrix. Versus in an adjacency list, in order to answer that question, you have to say, okay, what are all of the vertices adjacent to A? Is this one D? Is this one D? Is this one D? Etc. You loop through all of them, and either you find vertex D and you know there's an edge, or you don't find vertex D in case you know there's no edge between A and D. So it can be a little slower to determine if there is an edge between two different vertices. What if we want to do all edges between two specific vertices? Well, using an adjacency matrix, I would need to loop through an entire row in my graph or an entire column to know whether or not there's an edge between two vertices. So you can imagine that's kind of O of V time to get all of the vertices connected to any given vertex. Versus if I'm using an adjacency list, I can get that list of adjacent vertices back in O of 1 time. If I want to actually loop over all of them, then that's a little bit slower to do, but it still is faster than an adjacency matrix because I never have to look at unnecessary vertices. I only get back a list of vertices that are actually connected. Now the real big difference in efficiency comes in with where I want to add a new vertex to my graph. If I'm adding a new vertex to my graph using an adjacency list, I just add a new entry to my hash map saying, okay, this is my new vertex, these are all the vertices it's connected to. Maybe I have to update if I'm adding new edges, I have to update all of the other vertices in there, but those you kind of consider that's adding a new edge, not adding a new vertex. Adding a new vertex is really fast in an adjacency list, but the issue is if I'm trying to add a new vertex in an adjacency matrix, well, I have to create an entire new row and an entire new column. And the issue with that is arrays, to resize them, you have to create an entire new one. So in order to actually expand my adjacency matrix, I have to create an entire new adjacency matrix, and that's going to be O of V squared time. 1 second. Sorry, someone asked. Sorry about that. Someone just asked me a urgent question. All good. So adding a new vertex to an adjacency matrix is really slow because you have to recreate the graph. But adding a new edge is very fast. That's just flipping one of the spots in the adjacency matrix to a different number. So like from 0 to an actual weight. Adding it into an adjacency list isn't that slow because you need to append onto a list inside a map, and those are kind of both O of 1 operations, but it is much faster, kind of, if you think about it, what you're actually doing, it is much faster in an adjacency matrix. So those are kind of the differences between the two. I've got another question. LCS, if I switch the order of the strings on the 2D array, one on the vertical, one on the horizontal, we will get different subsequences. Is this correct? Like in your current example, if I do survivor on vertical and service on horizontal, we potentially get different subsequences. So about that, first of all, some strings will only actually have one valid subsequence. I believe that these two strings only have one valid LCS. So no matter what we do, we'll always get the same answer. I'm not sure. We changed this example last minute. But you are correct that depending on how we do the backtracking to actually determine the LCS, it can matter which order we have these two in. But that really depends on two things. A, which order we have them, horizontal and vertical, and B, which way we go back through when we're reconstructing the LCS. And if we switch either of those, then that would potentially give us a different LCS if there were multiple that we could have gotten. So, with that said, let's get to this example. The first thing I like to do when I'm doing all of these LCS examples is I like to go and mark every box that represents a match between characters. I think that's a really good first thing to do. So, here I have these two S's that match. Nothing with the E. I have these R's here and here. I have the V's that match here, here. The I's match here. There's no C and there's no E. So these are all of the boxes where I have a character match. And that's just going to make filling out this table a lot easier. So let's do it. Remember, our process is if we have a character match, we go kind of up to the corner right next to it and increment that value by 1. So right here, we immediately start with a character match. So we go to this diagonally adjacent one, that's a 0, increment it by 1, and that means we should put a 1 here. Now, for all of the rest of the things in this row, there's no match. And when there's no match, that just means we take the maximum of the thing right above me and right to the left of me. And you can see for this entire row, that's just going to be copying this 1 all the way across. So since I know that there's no more matches in this row, because I marked them all at the very beginning, I can just copy the 1s all the way across. Likewise, for this row with the E's, I have no character matches, so I'm just going to kind of copy this 1 down to the row below it. And that's kind of one little strategy you can use in LCS, is if you have a character here that doesn't appear at all in this string, you can just copy this row straight down. That always works. So now we get onto this R. These two 1s, because there's no match, works fine, but now we get to another character match. I know we're here because I marked it earlier. This is makes it really easy to not accidentally miss an edge, which is going to sound really, miss a match, which is going to sound really stupid if I did miss a match by accident, but I think I'm good. So, we get this match, so we look at this up left corner and add 1. That means we're at a 2 here now. So for the rest of these no matches, we can just copy that 2 across. We get to another match here. You'll notice we look at the up left corner, add 1 to that, and that's a 2. In this case, it's the same as if we didn't have a match on that character, and that's fine. It's not guaranteed that a match actually means something different. It just means that it might be a character that you have to use. We're just considering it for now. Now we move on to the next row. For these first couple values, we just copy the thing straight from above it because there's no match yet. Now we get to our first match. We look at the value right here, and we increment it by 1. We copy that over. Here is going to be like the same thing as over here, where we increment this 2 again. So these 3's actually kind of represent different things, but this 3 is going to be more important because you see it kind of ends on a corner. And that's really the intuition of when we're trying to build an LCS, we want to use the earlier characters because that gives us more characters to use for later in the pattern. No matches here, so we copy over the 3's. On this I row, we fill out everything before the match with just the row above it. This match is going to increment this 3 up to a 4. And that 4 remains for the rest of the row. And then finally, for these last 2 rows, since there's no character matches, we can just copy the rows down as they are. And you'll notice I've circled that. I love this shirt, but this microphone does not stay clipped onto it. You'll notice that I've circled the thing in the bottom right corner. That represents the length of the longest common subsequence between these 2 strings. It's always the value in the bottom right corner. I really hope I said bottom right both times, but bottom right is the answer. Now, next we're going to go back through this table and figure out, okay, what is the actual longest common subsequence? So in order to do that, I'm going to draw borders around my different zones. So that means that around this, I'm going to draw kind of a border around all the 4s. I'm going to do the same thing around all the 3s. And I recommend you do this if you're doing a diagramming question or something on paper. But just draw outlines around the different numbered sections. And now we can go back through and find our LCS. I'm going to use the red marker for this because I just used blue to draw the outlines. So what we do is we start here in the bottom right corner. Then we're going to alternate going as much up as we can and as much left as we can until we reach one of these corners. So in this case, it doesn't actually matter because there's only one valid LCS, but I'm just going to choose to go up first and then left. So this means that I start here, I go up. Here I hit this wall at the top, so I can't go any more up. So now I go to the left, and I reach this corner. What I do when I reach a corner is I take the character at this spot, so that's the I, and I write it down. You can see right here if I write something. So I write the I down, and then I move diagonally. So the only time I move diagonally is when I reach one of these corners and I add a character on. Otherwise, I only move up and left. So here, I would try to move up, but I can't. I would try to move left, but I can't. So I've reached another corner. I can add this V. When I add characters on this way, I'm adding them on backwards because I'm going backwards through my strings. So this V actually goes here before the I. And then I go diagonally again. Again, I can't go up anymore. I can't go left anymore. So I'm going to do another diagonal movement. This character you see is an R. So I add the R onto the beginning of my string, move diagonally. Now I'm going to go up as far as I can, left as far as I can. I reach another corner, so I add this character, and I go diagonal. And as soon as you go diagonal and hit a 0, then that means you can stop because there's no more character matches beyond that point. In this case, it was at the top left corner anyway, but that doesn't always happen if these first characters aren't the same. So you'll notice I've found that the longest common subsequence of survivor and service is SRVI, SRVI. So this is how LCS works from a diagramming sense. Again, I recommend you kind of mark the matches before you start, fill out the table, and then go through it backwards like this. If you had chosen instead to go left up instead of up left, that will sometimes give you a different longest common subsequence, just like sometimes flipping the two strings can sometimes give you a longest common subsequence. Not always. This string only has one LCS, so you're obviously not going to get anything different, but in some strings you might. In general, on exams, we like to give examples that only have one LCS because it makes it a lot easier to grade, but you could definitely encounter situations with multiple LCSs. I will wait a bit for you guys to ask some more questions, and then we'll move on to Quicksort, which is probably going to take most of the time we have left. So I've got a question. What's the point of finding an LCS? Wouldn't a search want to find a match with a Boyer-Moore or KMP type algorithm? As Dr. HB, I believe, mentioned in one of like the weekend review things, it can be sometimes useful for DNA sequencing to find kind of areas in two long strings where you have points of overlap or you have sequences that repeat. As for other applications outside of DNA sequencing, I'm not too sure about. I'm sure you can find some of those. But also we mostly introduce LCS because it's a relatively simple example of a dynamic programming algorithm, and you will encounter dynamic programming later on. You'll actually probably encounter other algorithms that will function similarly to LCS later on. So it's kind of a good way to give this introduction. Just like we give skip lists as an introduction for randomized data structures, LCS is a really good introduction into dynamic programming and this strategy of tabulation. But now I'm not seeing any more questions, so we will move on into the final stretch, or what will probably be the final stretch. And that's Quicksort. So I've kept these I and J pointers since pattern matching, so we're going to hope they still work decently well. Probably should have given myself more room here. A question, how does LCS help with graphs? Like, what would the graph representation of that be? I'm not really sure that you should or that you could or should represent an LCS problem as a graph. You probably could, but LCSs are completely separate from graphs. It's an entirely different topic. Graphs are in kind of like the graph algorithm section of the course. LCS is in dynamic programming. I'm just talking about them right after each other because that was the order that people requested for what they wanted to talk about. But you should not really think about LCSs in terms of graphs. If after you take algo, you might be able to find some kind of DAG representation of an LCS, but that's definitely not something for this class. Okay, Quicksort. I'm going to run through an example and do my best to explain things as I go. I think this is the same example from the previous recitation, but I'm going to again do it on the board fully instead of using the visualization tool. So the first step is we choose a pivot. In this case, I'm always going to just have the pivot be my first element because that's one less swap I have to do. It's essentially random. Obviously, choosing a random pivot helps to get better efficiencies, but this is just going to make the writing faster and helps it make more consistent. So 3 is my pivot. I've got my I and J pointer set up. Remember that I is the thing looking for large things. I wants to move large things to the right side of the array where they really belong. I is basically patrolling to make sure the only thing on the left side of the array are small things. So right now I started at 1. You'll see 1 is less than 3 though, so that's in its correct spot. Now I can move over to 6, and since 6 is greater than 3, I is going to stop because it wants to try to put 6 on the right side of the array. Likewise, J is doing the exact opposite. It's looking for small things that should go on the left side of the array. Right now it's starting at 5. Since 5 is bigger than our pivot, it's perfectly fine. It's in the right spot, and we can move J down to 2. Now we see that 2 is smaller than our pivot, so 2 is a small element, and we want to put small elements on the left of our array. So I has found a large element to put on the right, and J has found a small element to put on the left. So what are we going to do? We're going to swap them. And I see another question about LCS. I didn't quite catch what I said about what I mentioned to determine between multiple LCSs. Do we just go left, up, and up, left, and that will find all possible cases? Not necessarily, because I think in really long strings you can have cases where like going up on some of the cases and then left on others gives you LCSs. So you're not guaranteed that you'll find all of the LCSs by backtracking like this, but there will always be some kind of path you can go through the LCS table to find them all. Again, this is an algorithm to find one of the possible longest common subsequences. You're not necessarily going to find all of them. finding all of the longest common subsequences is kind of a different problem. So, we found our two elements to swap, so let's go ahead and switch them. I will move I and j down and rewrite this array. 3 is still our pivot. This is now a 2 because we've swapped it. This is now a 6. And now what I'm going to do is I and j don't need to be exactly where they are because they just swapped. We already know that we just put a small element on the left and a big element on the right. So we can automatically increment I and j without doing an extra comparison. And that can let us save a little bit of time on this algorithm. But let's keep moving I and j. I starts here, and again, it's looking for big elements to send to the right. So it stops at 4 because 4 is bigger than the pivot. J is looking for small elements to send to the left. 8 is not small compared to 3, so we keep moving j down until we reach 0. 0 is smaller than the pivot, so these are going to be the elements that we swap with each other. So I will rewrite the array. And just like before, we can automatically increment I, which puts it here at 4, and decrement j, which puts it here at 0. Now, before we do any comparisons, we make a note that I and j have crossed each other. This means that we're all good. Everything to the left that's small has been found, and everything to the right that's large has been found. So we know that we can place the pivot into its correct position. Now, some people always get a little confused about, okay, where exactly is the correct position? Because we have this I and j. And the important thing to note is, when we swap it, we have to look at the element that we're about to swap it with. Remember, j is at a small element, and I is at a large element. And when we swap with the pivot, since the pivot's at the beginning, we're swapping an element to the beginning. And we want to swap a small element to the beginning, otherwise we ruined all of the ordering we just did. So since j is at the small element, we're going to swap the pivot with j. And that's kind of a way you can remember, okay, do we swap with j or do we swap with I? You swap with j because that's the small element. I'll take these I and j off for now. I will indicate that we've got 0, 1, 2, 3, 4, 8, 6, 5. And now I will mark 3 because we've just swapped it into its exact correct space. Since we know that everything to the left of it is smaller and everything to the right of it is greater, by definition this means that 3 is in its correct place in the sorted array. There's nowhere else it could possibly go. So it never needs to get moved again. So now all we need to do is focus on the left side and the right side of the array. It's these little subarrays. And all we're going to do is we're just going to recursively use Quicksort to sort each side. So let's look at this 0, 1, 2 for now. And when I rewrite it, understand that this is all being done in place. I'm not actually creating a new array here. I'm just modifying just this 0, 1, 2 part of my array. I'm actually not going to draw the little right border just to indicate that it's not actually the end of my array. So, just like last time, I'm going to choose the first element to be the pivot to save some time. And I'm initializing my I and j pointers. I is right after the pivot, and j is at the end of my subarray. I wants to find large elements. 1 is larger than 0 already, so it's good. J wants to find small elements. Well, 2 is not smaller than 0, so we move back by 1. They're overlapping, that's perfectly acceptable. 1 is not smaller than 0, so we move j again, and they've crossed. Crossing is not fine. Crossing means we stop. We never do a comparison after they cross. Since they've crossed, we can swap the pivot with index 0. So, this is going to be a lot of circles. But we essentially swap the pivot with itself to indicate that it's now in its correct position. And we're left with really the exact same thing we started with. 0 in its correct spot, 1 and 2. So now we would make a recursive call. We would try to make a recursive call on the left side, but there's no elements to the left to make a recursive call with. So we make a recursive call to the right side. So we just have this 1 and 2. So if you want, you can hard code this in as an edge case instead of actually running the quicksort on it. But I'm just going to I'm going to run quicksort normally, choosing 1 as my pivot. Initialize my I and j pointers. The element right after the pivot is 2, and the element at the end of my subarray is 2. So I and j start at the exact same point here, which means I need to figure out which one to move. I wants to find large elements, which it has, and j wants to find small elements, which it hasn't. So j is going to be the one to move here. Now they've crossed, so we swap one with itself. So I draw 2 circles to indicate that it's swapping with itself. And we're left with 1 in its correctly sorted position, and then 2, which is now a 1-element subarray. And 1-element subarrays are always sorted and done. And remember that the 0 was actually here the whole time, and that's now correctly sorted. So now we need to handle this right side of the array, this 4, 8, 6, 5. So let's take a look at it. Four is going to be the element I choose as my pivot. Not a very good pivot, unfortunately, but we'll get there. I initialize I and j. I is not going to move because 8 is already larger than 4. So j is going to move all the way down until it crosses, because none of these elements are less than 4. Just like before, we swap 4 with j, which is itself. And that's going to give me 4 in its correct sorted position, then 8, 6, 5. Now we do this again on the, you see the left side of this is nothing, so we only call a quicksort on the right side. I'm going to choose 8 as my pivot. This one's going to be a little different. I initialize my I and j. In this case, I wants to find an element bigger than 8. 6 isn't bigger than 8. 5 isn't bigger than 8. So we go past. And this is why it's so important to always stop as soon as these 2 pointers cross. Because if I didn't stop right here, I would get an index out of bounds exception. But by stopping before I do a comparison, I can prevent that. And this means that I swap the pivot with index j. And what I'm left with is 5, 6, 8, where 8 is in its correct sorted position. Now, you've already seen exactly what it looks like when I try to do quicksort on these 2 elements, so I hope you'll just let me save the time and indicate that we know that these 2 elements are in their correct positions already. They would only end up swapping with themselves a lot. And we know that this 4 is right. So if I bring everything down into this array, you can see that I forgot 3. But otherwise, every element is correctly sorted, and we now have a sorted and slightly squished together array. None of this was out of place. We never created any new arrays. All of these only took place inside the original array. We created nothing new for this, and we have a completely sorted array. Now there's only about 5 minutes left. I'm going to say that's not enough time to cover an entirely new topic, but I will stick around for a little bit to answer some questions. Otherwise, if there's no questions after like a minute, after like 2 minutes or something, I will go ahead and stop the stream early. But otherwise, it's been a great recitation, guys. Alright, I haven't gotten any new questions, so I think, as you can see my face. Alright, haven't gotten any new questions, so I think this is roughly where I'm going to end it. Something I want to mention, I've noticed the people that ask questions this week, we also put like timestamps of when you guys ask your questions. I trim off, when I upload these, I do trim off the very beginning when it's only playing that music. Hopefully you guys enjoyed that music. The track is I Don't Want to Say Goodbye from Pokemon Mystery Dungeon. I love the song. But that kind of shifts the timestamps by like 20 minutes. So I'm sorry if that isn't really the time, if the timestamp of your question doesn't really match up anymore. That's just mostly to save time. So you don't need to skip through 20 minutes of nothing to actually find when the recitation starts. Otherwise, as I said in the beginning, please fill out the Thank a Teacher thing for any of your TAs that helped you, especially the TAs that you had before this whole mess started, because there's not really a SIOS where you can give us feedback or anything. So if you really enjoyed your TAs, please send them your thanks. We really appreciate it. I see a thank you in Piazza right now. Thank you. I'm not going to say your name on stream, obviously, but thank you for your thanks. I see it. I love it. Please, thank you. But thank your other TAs, especially the ones that don't get to be in the spotlight all the time. I was very fortunate to be able to actually give these recitations to you along with Landon. But a lot of the other TAs have still been doing a ton of work to help out with these. These recitations would not be possible without many other TAs. All of the people managing chat, Ivan for making these beautiful layouts and other graphics. I do have an actual question. Do we need to know under what condition each graphing algorithm works better? You should understand like the basic idea of like BFS, DFS are algorithms to go across the entire graph. Dijkstra is the shortest path. Prims and cross-skulls are for MSTs. But I wouldn't say that you really need to know like, oh, when is BFS better than DFS or vice versa. That's really a 3600 or like more of talking about like graph theory and graph search problems. So it's mostly going to be about when each category of algorithms works, not when each algorithm within a category does. But with that, I think I'm going to go ahead and call it quits on my final recitation. It's been a ride. Thank you all for being supportive and helpful. And good luck on your final exams. You guys will do great. I know. It's been a rough time, but you guys have made it through beautifully, and you guys are going to kill it out.